Hey everyone, and welcome back to The Explainer. So think for a second about how you actually experience the world around you. You've got eyes to see, skin to feel temperature and pressure, ears to hear. Well, modern machines and automated systems, they need to interact with the physical world too. But to do it, they rely on an incredibly complex array of mechanical and electrical devices. Today, we're diving into the fascinating world of sensors, literally, the senses of the machine.
All right, here's our roadmap for today. We're going to start with the senses of machines, then cover measuring heat flux, microsensors and MEMS, resistive sensors, and finally wrap up with the rise of smart sensors.
Okay, part one, the senses of machines. Let's get into it.
Now, right off the bat, let's tackle a question that honestly trips up even seasoned engineering students when they first get into this. What is the actual difference between a sensor and a transducer? People use these terms interchangeably in casual conversation all the time, right? But in engineering, they have fundamentally distinct roles. Getting this straight is the baseline for literally everything else we're going to talk about. So, a sensor is essentially your detector. It's the physical body that reacts to a change, whether that's a physical, chemical, or biological condition in the environment. It just senses that something happened. A transducer, on the other hand, takes that reaction and actually converts the energy from one form into another. Think of the sensor as your skin feeling the intense heat of a stove, and the transducer as your nervous system, turning that feeling into an electrical pain signal that shoots up to your brain. While a sensor might detect a mechanical change like pressure, the transducer converts that into a usable electrical signal that a computer can actually read. Moving right along to part two, measuring heat flux. Let's look at our first major classification, thermal sensors, specifically heat flux sensors. By definition, a heat flux sensor is a transducer that measures the rate of thermal energy transfer per unit area across a surface, and that transfer can happen through convection, conduction, or radiation. When it's exposed to that thermal energy, the device generates a voltage signal that is directly proportional to the heat flow. This isn't just academic theory either. It's incredibly useful for optimizing thermal performance in everything from basic home insulation to rigorous aerospace fire resistance testing. And the architecture of these devices brilliantly illustrates how this works. You've typically got constantan and copper wiring running through a filling material, which creates distinct hot and cold sides within a flat plate sensor. It's designed to measure the local heat flux density in a single direction, perpendicular to the surface. It's exactly that temperature difference between the hot and cold junctions that creates your readable signal. A really classic example of this is the Garden gauge, and its working principle is just fascinating. Let's break it down step by step. First, the center of a circular metal foil is exposed directly to a heat source. Second, the outer edge, the periphery, is intentionally kept cooler. This creates a really distinct radial temperature gradient from the hot center out to that cool edge. Finally, a thermocouple junction placed strategically between the center and the edge generates a measurable voltage based exactly on that temperature difference. It's an elegant physical reaction translated into readable data. We're literally turning heat into math. Now, a lot of the time, these thermal sensors use multiple thermocouples connected in series. We call those thermopiles. But, every engineering choice comes with trade-offs. On the plus side, thermopiles give you excellent stability, a low ohmic value, meaning they don't pick up much electromagnetic interference, and a really great signal-to-noise ratio. Plus, zero input naturally gives zero output, so no false readings when it's at rest. The main drawback, though, they suffer from relatively low sensitivity overall, so they aren't ideal if you're trying to detect very faint thermal changes. All right, part three, microsensors and MEMS. Let's scale things way, way down to see how this builds into something even more advanced. We're talking the microscopic scale here with microelectromechanical systems, or MEMS. Because they are microscopic, use barely any power, and are super cheap to produce, their real-world applications are absolutely massive. They're actively used in environmental monitoring to track air quality across entire smart cities. In cars, they are the secret sauce behind stability control and adaptive cruise. And in robotics, they allow for highly precise micromanipulation of super delicate objects.
Now, what's really interesting is how these microsensors handle pressure differently depending on their design. In some setups, physical pressure induces mechanical deformation in extremely thin silicon diaphragms. But in a capacitive sensing structure using Pyrex glass and silicon, it's a bit different. Instead of just measuring the physical bend, that diaphragm deformation changes the capacitance between tiny electrodes, so it converts physical force directly into electrical signals like changes in voltage with unbelievable precision. But there's a totally alternative working principle at this microscopic scale too, piezoelectric sensing.
Instead of measuring a flexing diaphragm, this relies on a piezoelectric disc sandwiched right between electrodes. When a mechanical force or stress is applied to the specific kind of material, it naturally generates an electrical charge. So literally, just by physically squeezing the material, it creates its own measurable electrical signal. No external battery required for the sensing element itself. It is incredibly efficient for things like structural monitoring or impact detection.
Which brings us to part 4, resistive and potentiometric sensors. Shifting gears completely to electromechanical classifications, let's talk about resistive sensors. A resistive sensor is a device that converts a mechanical change, think physical displacement or stretching, into a monitored electrical signal. This entire category relies heavily on one foundational formula: resistance equals resistivity times length divided by area. The actual resistance of the material in these sensors depends on 4 crucial things: its chemical composition, its operating temperature, its length, and its cross-sectional area. If you alter just one of those physical properties, you dynamically change the resistance. To really visualize how we measure displacement using resistance, think about a potentiometer. If you've ever turned an old-school volume knob on a stereo, you've used one of these. Basically, you have a fixed resistance element connected to a voltage source. Then, you have a sliding contact, often called a wiper. As the object we want to measure moves, it physically drags this wiper along the resistive element. By measuring the voltage output right at that sliding contact, we know exactly how far the object has moved. Pretty clever, right? But while they're simple and definitely cost-effective, potentiometers have some very tangible physical drawbacks. Because they rely on parts literally dragging against each other, they require a relatively large force just to move the wipers. And worse, those sliding contacts are fully exposed to the environment. They can get contaminated by dust, oil, moisture, you name it. They are prone to actual mechanical wear and tear over time. They can get misaligned from vibration. And as they physically wear down, they generate this frustrating electrical noise that completely disrupts the signal.
And that leads us to our final section, part 5, the rise of smart sensors. To overcome the limitations of purely mechanical or basic electronic sensing, the industry had to evolve, and we've arrived at the pinnacle of modern automation, the smart sensor. You see, a traditional sensor just sends raw, dumb data down a wire for processing somewhere else. But a true smart sensor? It's a whole different ballgame. It's defined by 3 things: the base sensor that captures the data, an onboard microprocessor that actually computes and analyzes that data internally, and built-in communications to share those processed analytics. It doesn't just feel, it thinks and it speaks.
You're going to see 5 main types of smart sensors driving modern environments today. Level sensors measure volumes for advanced fuel gauges. Smart temperature sensors act as watchdogs so heavy factory machinery doesn't dangerously overheat. Pressure sensors continuously monitor fluids to hunt for invisible pipeline leaks. Infrared sensors are absolutely crucial in medical gear like pulse oximetry to monitor patient health. And proximity sensors? Retailers use those actively to track customer movements and optimize their store layouts. Of course, deploying smart sensors comes with massive benefits, but also some pretty serious challenges. Because they process data internally, they offer incredible energy efficiency and give you real-time access to data in remote or dangerous environments. But because they are networked computers, their biggest drawback is their susceptibility to cybersecurity hacking. And that is a major concern when these sensors are controlling power grids or vital city infrastructure. On top of that, the initial setup costs are high, and doing maintenance out in remote settings can be exceptionally tough. So the crucial point here is that despite those cybersecurity risks and the high costs, these devices are the absolute driving force behind Industry 4.0. They are the backbone of the next industrial revolution, allowing highly complex factories to self-diagnose their own issues, control their manufacturing processes, and react to real-time variables, entirely without human intervention. As our source material beautifully summarizes, the smart sensor is also a crucial and integral element in the Internet of Things. It is exactly this tech that lets us provide a unique digital identifier to almost any physical object in our world, transmitting data across the global network and ultimately giving the digital realm its physical senses. We've journeyed from the basic physics of thermal transfer and microscopic piezoresistive diaphragms all the way up to networked microprocessors making autonomous decisions. But it leaves us with a really critical question to ponder. As our machines gain ever more sensitive and connected senses, how will this ultimately reshape the security and automation of our physical world? The sensing technology is already here, but how we protect and apply it, well, that's completely up to us. Thanks for joining me for this explainer. Keep learning, and I'll catch you in the next one.